Okay, so I'm going to try to talk a little bit about how I think about these, and it looks like your guys probably talking about it a little bit different, but this was the way I was taught to think about it, so it's the way I do think about it. So if we think about that differential equation, I always think of it almost like a fluid, right? And so that fluid's not going to have any current when obviously the differential equation is equal to 0, right? Our rate of change is 0, so we shouldn't see any fluid flow, as I like to think of it. So essentially I'm thinking, when is this expression going to equal 0? And in this case we have a quadratic, so quadratics can come in 3 different flavors. Either you have 2 solutions, no solutions, or 1 solution, and it all depends on the discriminant. So I've got the discriminant written there in what seems to be a child's writing, but in fact it is mine. So remember the discriminant's just, and there I go again. B squared minus 4ac, that was my best attempt at an underline. So, and remember that if b squared minus 4ac is greater than 0, you get 2 solutions, and you can see it written here, right? If it's less than 0, none. If it's equal to 0, you get 1. So really all I need to think about is, look at this discriminant, and I did not mean to mark here. Look at this discriminant and think, for these different values of alpha, how can we get these different solutions? So just some notation, I just named the discriminant capital D. And, if we plug in the values, we see that our discriminant is essentially alpha squared minus 4. So, how can we get different solutions out of this? Well, obviously if alpha is 2, that makes the discriminant 0. Which means we got 1 solution. If alpha is bigger than 2, we'll get some positive value, so we'll have 2 solutions. Now, if alpha is smaller than 2, we're going to get no solution, except for if it gets small enough, which is to say if it gets to be negative 2. Notice, we're back at 4 minus 4, so you get 1 solution again. But if alpha is less than negative 2, well, anything less than negative 2, you square it, you get back to 2 solutions. That gets you get back to a positive answer. Okay, so we have all these different conditions on what alpha might be, and they all produce, different solutions. So I'm looking at what, I assume is the answer key here, and they've got all these different number lines, and those correspond to those different alphas, those different conditions on alpha, and they produce different solution states. So finally we've exhausted all our possibilities for alpha. So here's kind of how I go about thinking about drawing those number lines, those whatever they call them, phase lines, as they say. I like to think of it as a 2-dimensional graph myself. That's how I was always taught and how I was always shown. So I just kind of picked a particular example of alpha. So like alpha's 5, let's say. So that's obviously that second condition, right? Bigger than 2. And I just kind of worked it out, and I didn't show it anywhere, but I plugged 5 in for alpha, and then that makes that differential equation 0 at about 0.2 and 4.8. Obviously those are not rational solutions. I approximated those, but close enough. So what I usually do for these is I'll mark this off on a 2-dimensional graph. I don't ever remember drawing a phase line like this. We always kind of did a 2-dimensional thing with our bifurcation values or whatever, but same deal, I guess. But I like the visual of a 2-dimensional sort of dealio here. So notice what I did. I marked the first 0 on the y-axis, so I made the y values my y-axis and t values my x-axis here. So I've got this dashed line for my first equilibrium point. I've got a dashed line for my second equilibrium point. And then all I'm doing is I'm just kind of testing values in my differential equation. So for example, if I go down to I want to test a value below 0.2. 0 is a perfect one, right? Because it's really easy to plug in 0. And if you go back up to your differential equation, somewhere it's up here, scrolling. So if I plug in 0, right, I get a positive answer, which is that's a positive slope. So anything less than 0.2 is going to net me a positive slope. So if I think of this as a fluid, if I think of this as a fluid, then all of the, if I always think about maybe if I place like a small pebble or small rock, what's going to happen to that rock? Well, it's going to drift upwards because I know that my flow is trending upwards. So it's going to float up towards this equilibrium point because I know all the slopes down here are positive. It's going to push everything up towards this equilibrium point. Okay, and I got that from just testing a value. Tested 0. Okay, now let's test a value in this region, right? Notice that I basically broke the plane up into 3 regions. We already know what's going on down here, so let's test something in here. 1's the obvious choice, just because it's easy to plug in again. So if I'm in maybe, God, this is going to look ugly. I'm going to try to write my differential equation here. So it's y squared minus 5y, because I just arbitrarily chose 5 as my alpha for this case. Obviously, I just chose 5, but, any number bigger than 2 would have worked. So let's test 1. If I put in 1 here, well, I get a negative value. So you can kind of see how I drew that in. So anything that I would place in this region, again, I always think of this as fluid flowing. Like if I place a small object, where's the current going to take, that small object? It's going to push it downwards because all the slopes here are downwards. So you can see, basically no matter what I do on the plane, if I place something below 4.8, the fluid's going to push it to that 0.2 equilibrium point. Of course, if I put it exactly at 0.2, it's just going to stay there because there's no current there. So that's what we call a stable equilibrium point, because basically, if I put something on the line, it's not going to move. There's no current. But if I offset it just slightly, the current's going to work to push it back onto that line. Right? It's very nice and safe and stable. But now let's look at this on the opposite side of 4.8. So like 5, right? 5's a nice even number that I could test. If I put in 5 here, you'll see a positive value. 25 minus 25 plus 1, that's positive. So I get positive slopes. So all my flow is going to trend upwards. So let's think about what happens if I put an object on this 4.8 line. Right? If I put it exactly, if I'm really, really precise and exactly on the line, it's going to stay there. But if I deviate just a little bit, right? If I put it at 4.85, it's going to go off to infinity. If I put it at 4.75, it's going to go down to my 0.2. Okay, so that's what we call an unstable equilibrium point, because if I'm exactly perfect, I'm in good shape. But if I deviate just a little bit, that thing, whatever it is going to get carried off by the current to somewhere else. Okay, so it's unstable. So my phase line looks like what you see over here, where this equilibrium point, that first equilibrium point, is stable, so we shade it. The second one is unstable. And I can't remember. Let me look at the answer key here. It looks like he's drawn in, actually, the slope kind of direction. So it looks like I would mark this way, this way, this way. Just kind of marking in what we did what I would have done on a 2-dimensional grid. Looks like your guys are doing on a 1-dimensional line, which you can see it achieves the same effect, but it's just slightly different. Now, I got 0.2 and 4.8 because I chose that particular value of alpha. If I would have chose alpha equal 10, I'd get different numbers here. But regardless, whatever number I got here, the first one was going to always be stable. The second one's always going to be unstable. Okay, so even though I chose 5 because I like having a nice concrete number to work with, I wouldn't have had to have chosen 5. Any number greater than 2 would have produced the same sort of thing. It's just these numbers would have been different. And I know you said you didn't like graphing here, but I feel like, you don't actually have to graph this parabola to be able to do this. You just have to graph some, horizontal lines. So I think this is it gets you out of graphing just a little bit. And then really all you're doing is test points, right? And if you get a positive or negative, you can kind of draw your lines accordingly. So I'm going to go ahead and of course, you could do the same thing for any choice, for any of your conditions on alpha here, right? Like I could go and I could work my way through all of these, but I don't necessarily feel like it. But let's do one more. So now let's choose alpha equals 2. So again, maybe it's nice to think about what that turns our differential equation into. So then we'd have y squared minus 2y plus 1. And I think it might be beneficial to factor that in this case, because then you can see it's just y minus 1, the quantity y minus 1 squared. Okay, so, you know, obviously there's only one way to make that 0, and that's if you have y equals 1. Okay, so let's mark that off on our diagram. Okay, and then let's just test the value, right? Let's test 0. What happens if I put in 0? Well, I get a positive answer. And what happens if I put in 2? A number on the other side of the equilibrium point. Well, I get another positive answer. So I only have one equilibrium point, and it's unstable. So, and again, I'm thinking about this as being like a river or a fluid. If I put something right on the line, well, happy day, it's not going anywhere. But if I deviate just a little bit, it's going to go off to infinity. If I put it below the line, it's going to go to my equilibrium point, but then again, if I deviate just a little bit, it'll go off to infinity. So this is an unstable equilibrium point. Again, I have not been drawing in the directions of the slopes, but there we go. I guess I probably shouldn't put an arrow on both sides of my phase lines, so I should that way I can indicate a positive direction. So there we go. There we go. So I think that's the only 2 examples I've got worked out. But that's how you could do that without having to graph a line. So I would just have these little rough sketches off here. Mark off where dy dt is equal to 0, you know, for a given choice of alpha. And then just kind of test some points. Mark in your slopes. See if they're stable or unstable. And then just kind of draw your phase lines accordingly. That's, to me, the easiest way to do that without actually having to graph this parabola. Now, I will say, if you go to Desmos.com, it's a free graphing calculator, it'll actually let you put sliders in. So, like, you could literally type in y squared minus a, it doesn't have Greek letters, ay plus 1, and then it'll make a slider for you, and you can actually play around with this alpha term, right? So it'll throw the graph up there on you. So obviously it's going to be a parabola, okay? But it'll throw the parabola up there on there, and as you deviate alpha, it'll drag this parabola, you know, up and down and left and right. You'll be able to see this move, and you can kind of see these equilibrium points pop in and out of existence, it's kind of a neat thing. And it's, you know, it's easy, but don't help you on a test, because I doubt you'd be able to use it on a test. But as far as homework goes, that may be a good thing to go to. So again, that's DESMOS.com. I cannot spell without a stylus, it turns out. So anywho, that's my spiel on differential equations and phase lines, I guess.